So we are going to discuss about the moment of inertia of uniform rod. Now here is a rod and the mass of this rod is m, mass of rod is m, and the length is L, and the mass distribution is uniform, and we need to find out the moment of inertia. And first of all, we cannot define the moment of inertia unless there is some axis or some point is given to us about which the object is rotating. So let's find out in this case, in the first case, let's find out the moment of inertia of this rod about the center of mass. Okay. So I am going to take the center of mass axis as the axis of rotation, right? And you know very well that for a uniform rod of length L, the center of mass will be at the midpoint or from a L by 2 distance from the end, right? So it will be at the L by 2 distance from any of the end. This distance and this distance is L by 2. And this rod is rotating with omega about this axis with omega. We need to find out the moment of inertia. So just think it how we can calculate. We have discussed about the formula of the moment of inertia for the continuous bodies. I think you remember it, right? What is the formula? The formula I is integration of r square dm, where r will be the position of r will be the perpendicular distance of the point mass and dm will be the point mass, right? Okay. So first I need to take a point mass or a elemental mass. I need to define the r for that, dm for that in terms of r, and then I will calculate. Okay. So now this is a rod. For this rod, the mass is distributed on the length. Okay. So there is a linear mass distribution. So first of all, I can define a linear mass density. Linear mass density, let me write down, the linear mass density is the mass density per unit length will be equals to total mass divided by length, because it is a uniform rod. Okay, will be represented by lambda. Okay, so lambda is just a constant for any point. And now I am taking a elemental mass somewhere here. This is a elemental mass. Okay, let's take the elemental mass at a distance x from the axis of rotation, and the thickness of this elemental mass is a dx. These are the values. So just think it, why I am taking like this, why I am not taking at an angle theta a mass of dm in terms of theta or something else. Just think it, why I am taking only like this. You will come to understand that we cannot solve this question in any other way. We need to take it like this, then only we can solve. We need to take the elemental masses in terms of the thickness, right? We can assume this rod to be formed by a small element of dx by using the combination of these elements, right? That's why I am taking it. And this will be the thinking process for calculation of any kind of moment of inertia for the continuous mass distribution. So you need to understand why I am taking like this only, why not by any other way, right? If you can understand that, then you can solve many other questions related to this. Okay, so let's go again on this and let's solve it. So let's find out the dm. So dm is the mass density multiplied by thickness, lambda multiplied by dx, right? Okay, this is the mass of element, and the perpendicular distance will become equal to x. Okay, and now let's place the value into this equation of continuous mass distribution. So I is integration of x square lambda dx. Now this is a finite rod, so I need to also define the limit from where I am starting or where I am taking the first element, and from at where I am ending, where is the last element. So this will be our first element, right? And this will be the last element. So for this element, for the first element, the location will be minus L by 2, and for the last element, it will be plus L by 2. So let's substitute the value and find out the I. I is L by 2. Okay, sorry. So it's lambda, let's take out from the integration x square dx, and the limits are from minus L by 2 to L by 2. Okay, so integration of x square is x cube divided by 3, and lambda, let's substitute it as m by L, so that is and x cube divided by 3 minus L by 2 to L by 2. And now let's substitute the limits. So m by L, if we substitute first L by 2, it will be L cube divided by 24, and minus plus, because in one minus will be there with the x cube and one with the lower limit, so it will become plus L cube divided by 24. Okay, so I will be m by L cube divided by 12, or you can say ml square divided by 12. So I is I for the rod about the center of mass axis and perpendicular to the axis of the rod. I will be ml square divided by 12.